In this video, we're going to look at some examples of integration from a physics perspective. And we're going to start by examining material property. Let's imagine we have some material. Now, this material, I set an extension and measure the restoring force. And then I set a new extension and measure that restoring force. And I set a new extension and I measure that restoring force. And I do that over and over again. And I plot the results on a graph with the force on the y-axis and the extension on the x-axis. And perhaps the points form a graph that looks a bit like this. Well, one of the things we can do is try to pick a function that matches what we can see in our results. So I did some fiddling around, and let's say that I came up with this expression here. You can see that equation is a cubic with a quadratic term as well. I haven't tried to give an explanation for this relationship. I haven't delved into the physics to have a look at what's going on within the material. All I've done is looked at my results, picked a function and thought, yeah, that looks about right. And that's what I've got here. There are very sophisticated software packages that can do this for you. And to a limited extent, even Excel can do this for you. There's some interesting things you can do now you've got an expression. If, for example, the material broke when it had 12 units of this extension, whatever it is, then we could work out the maximum force by differentiating this function and setting the derivative equal to 0. That's where the gradient is 0. We would get a quadratic, which we could then solve. We'd have two roots of that quadratic. One would be this root, and one would be this root. So there's things you can do with differentiating, but that's not what we're looking at in this video. In this video, we're looking at integration. And so let's calculate the work done in extending this material to some amount. Let's say 12 units. The extension here is an x on the x-axis. Well, let's write that equation onto our notebook and then we can integrate it. And here it is. This is our force as a function of the extension. And it's got constants a and b. The expression for the work done is the force multiplied by the displacement. And here it is. The displacement is the extension. Because the force is a function of the displacement, the extension, I've had to write it like this. That means I'm going to have to integrate this. Now there's the expression all written out. And you can see I've got a function of a function that I'm going to try to integrate. Well, each of these terms can be multiplied out. Because right now there's just too much going on. Well, I always find it easier to write things out full. So let's start with the bx plus a all squared. I write that as the two brackets, bx plus a multiplied by bx plus a. And then I multiply out the different terms. So bx multiplied by bx is b squared x squared. A multiplied by bx is abx, but I've got two of those. This one and this one. And then finally, the a multiplied by a is a squared. Now, cubing means I multiply by bx plus a again. So I take the bx plus a and I multiply it by another bx plus a. So we have b squared x squared times by bx is b cubed x cubed. A multiplied by b squared x squared is a b squared x squared. B times x multiplied by 2abx is 2ab squared x squared. A multiplied by 2abx is 2a squared bx. Bx multiplied by a squared is a squared bx. And finally, a multiplied by a squared is a cubed. Now looking at this, we can tidy some of this up. Just like that. One lot of ab squared x squared and two lots of ab squared x squared makes three lots of ab squared x squared. Two lots of a squared bx and one lot of a squared bx is three lots of a squared bx. Well, I've written the expression, but it's taken up quite a lot of space, so I think I need to zoom out a bit to get it all to show. Maybe a bit too far. Okay, there we have it. So that is the full expression for extending this material by an extension x. And I hope you can see where all these terms come from. There's quite a lot of terms here to rattle through, so I'll do it quite quick. This term is integrating this term. This term is integrating this term. These two terms. These two terms. This term, and it's a minus. This term, and it's also a minus. This term, yet another minus. This term, and finally, that term on the end there. Now we can go through step by step and calculate what each of those is. So the b cubed, that's a constant, that comes outside. Integration, you increment first, so this becomes x to the 4, and then we divide by the new power, 4, plus 3ab squared, that's a constant, that comes outside, x squared, integration, so first we increment and then divide by that new power. Okay, so 3a squared b comes outside because it's a constant, the x we increment and then we divide by the new power. A cubed comes outside, and then that an integral dx is just x minus b squared, increment the power, divide by the power, minus 2ab, increment the power, divide by the new power. You can see how straightforward this really is. And then this just becomes x, because integral dx is just x. And then finally, this thing over here, that's also just an x, but it's 5 of them, so 5x. And then we've got some constant at the end, which I'm going to call c. And the last step would just be bringing together like terms. So b cubed over 4, x to the power of 4, that's just the only x to the 4 term. But there are two x to the 3 terms. There's this term here, and then you subtract this term here. And doing so and factoring out the x cubed gets this term here. Then we do the same thing with the x squared term, so 3a squared b over 2, then minus 2ab over 2, that's x squared. And that came from this term, subtract this term, and then factor out the x squared. Finally, terms with x in it, so we've got plus a3, a to the power of 3, minus a squared plus 5, and then some constant at the end. Now, if we want to find out what the work done is, we're going to put in a value for x, and c is going to be 0, because what we're essentially doing is finding a difference between two values. One, when we are at the top limit, with whatever x is, the other when x equals 0. So this cancels out the c. Whenever we have a definite integral, that c will vanish. It's there at the moment, but it will vanish if we do a definite integral. So yes, it's a long, grungy expression, but we can just put our numbers in now and do the calculation. Do you remember what those numbers were? Well, we had b was 0.2 and a was minus 1.43. And we were working out the work done in extending this to 12 units, whatever units those are on the x-axis. And that will tell us how much work has been done in whatever the energy unit is, which would be the unit of the y-axis multiplied by the unit of the x-axis. So I've done some grunt work with my calculator, and this term here is 41.42. Then this term here is minus 121.9. Then this term here is positive 129.5. This term here was just 0.3707. Remember, c is 0 when we use definite limits on our integral. So our answer came in at 49.39 of whatever unit we've got. Now, I've put here units squared because we're multiplying the y-axis by the x-axis, but they won't be the same unit. On the y-axis, it was some sort of force, if it was newtons, and if the x-axis was in meters, then that thing there wouldn't be units squared, it would be joules. I don't know what unit of energy that is, so I've just written rather oddly just units squared, because on my graph, there's no units. So whatever units are on the y-axis, it looks like it's the same units on the x-axis, on this very abstract case. Now, just a little note about what you might be asked to do in an exam would be to find the area under this line, between the line and the x-axis. In A-level, you'd do that by counting the squares. So I went ahead and counted the squares. Each of these little squares is 1/2 multiplied by 1/2. 1/2 a unit in the x direction multiplied by 1/2 a unit in the y direction. So that's a quarter of whatever these units of energy are. I counted up how many squares there were between 0 and 12 on the x-axis. And it turns out that there are 177 whole squares and there are 33 half squares. And when I added those together and multiplied it by the energy represented by a single square, which was 0.25 or whatever this energy unit was, it gave me 48.38 of this energy unit. You'll see that it's almost the same. It's only one energy unit difference. At A level, counting the squares to integrate, probably a bit of a time saver compared to doing all of this. You can also see why we would prefer to find an easier function. This function here wasn't an easy function to work with. It would be easier if we could find some exponential function or something that's quite straightforward to integrate. Okay, let's look at the case of a skydiver. So here I've modelled the motion of a skydiver using this equation here. Remember, it's just a model. The initial acceleration is about 10 meters per second per second. The y-axis is the velocity in meters per second. The x-axis is time in seconds. The terminal velocity I've chosen as 56 meters per second, which seems about right for a person that's falling through the air. And so I've got these constants that I've chosen to fit what I observe. Now let's suppose I want to work out how far the skydiver falls in 30 seconds. Well, to do that, I'm going to have to integrate this function. And you can see this time I've been a little bit more careful about these units, so we can get some meaningful answers from this. Well, let's explore some things we know to see if we can solve this. We know that if we differentiate e to the mx, we end up with m e to the mx. It's a general form. So if we integrate, we work in reverse. We're essentially dividing by whatever it is that is before the x. In our case, it's not x, it's t, and we're going to be dividing by minus n. And so we have that. What else do we know? Well, we know we could write our function like this instead, which means that when we integrate it, we can break it apart into these two terms on the right. A is a constant, so we know that in both of these cases, we can take that constant outside the integral, like this. And now you can see it's much easier to solve. The integral v dt, that is what the displacement is. The integral dt is just t, and there will be a constant of integration, but because we're going to use absolute limits on this, I actually don't need to worry about that. I will include it at the end. A constant from this integration and a constant from this integration, when subtracted, just gives you a different constant, so I'll leave that until the end. Let's add that constant on there. Now you'll notice this has gone positive, and that's because we had a minus here, but then we also have a minus from the integration. Now I can just plug these numbers in, remembering this c is going to vanish anyway, and we are going from 0 displacement up to, just need double check because I've forgotten, 30. We're going from 0 seconds, should I say, all the way up to 30 seconds. So here I've substituted my numbers, and now I can just do this sum on my calculator. And there we have it, a whopping 1.681 kilometers. That's a big old distance to fall in 30 seconds. But that's what my model predicted. And if you look at the graph, it's not a bad approximation. I mean, I've used an exponential here because it was quite easy to integrate. But actually, because of how air resistance works, it's not going to be an exponential function. But you saw from the previous example why I might prefer an exponential over a polynomial. You can integrate polynomials, it just takes a bit more grunt work when you've got lots of terms. Whereas integrating exponentials, very, very straightforward. Now I decided to double check using that quick rule of thumb where we can count the squares. That's the way we would integrate in A-level physics. Each square here has a displacement of 2 meters per second multiplied by 2 seconds, so that's 4 meters. So I counted up the squares under the line, well, between the line and the x-axis, up to 30 seconds. And I got 289 whole squares and 39 part squares. And remember, we're going to count each part square as a half square. When you add all this together, multiplied by how far each square is, I should write meters per square, shouldn't I? That's better. I get 1,234 meters. You notice a little bit different there. It's not the same. It's about 27% smaller, so it's not great counting the squares. It will do, gives us a ballpark figure, but it is only an approximation. Unless I've made a mistake in counting the squares, and please do double check for me. I do make mistakes. But the whole point of this is we are modelling something that we observe with some sort of function, and you can see that over there, and we're using that to then calculate physical quantities that we're interested in. In this case, the displacement of a skydiver. And let's hope they open their parachute after 30 seconds. Now there's another integration rule that can be very useful for more complicated situations called integrating by parts. And we will have a look at that in the next video.